Hey everybody, it's Miss List, and I'm back with 5.6, which is on reaction energy profiles. These may look familiar to you. I know that I covered them in my on-level chemistry class. So if you've seen these before, great. If not, then that's okay, because they're not super complicated to analyze. On our y-axis for each graph, we have potential energy. And that is often going to be measured in kilojoules per mole. And then the x-axis is showing us the reaction coordinate, or the progress of the reaction. And we have two graphs, two examples here. One on the left is exothermic and one on the right is endothermic. Now, the difference between these is where we start. So if we look at the exothermic reaction, sorry, I'm trying to change my pen color. Exo means that energy is released, and that's going to be usually in the form of heat. So my surroundings are going to get hotter. Now, endothermic means that energy would need to be put into this reaction to make it go. So this is going to be an energy going in to the reaction. So I would have to heat it up or add energy. The surroundings in this case would get cooler in an endothermic reaction. So the difference between the graphs, if we analyze what they look like, when it's exothermic, my reactants, which here is on the left where I start, is going to be higher than the products. So my reactants are higher than my products. It's reversed when I have an endothermic reaction. The reactants start lower and the products are higher. And this overall change in energy, that's called the delta H. That means I'm going to have to put energy in to get this reaction to go. That's why my reaction is endothermic. I have to put energy into it. And my delta H, that change in overall energy, is going to be positive because I'm putting energy in. But when I look at the one on the left that's exothermic, I'm starting high and ending low. And that difference, that delta H value, is going to be negative. And the reason it's going to be negative is because that I'm starting high and ending low, and that difference in energy has to be energy that gets released. Now, the other thing to note on these graphs is something called the activation energy, which we talked about in our last section. That's the minimum energy needed for the reaction to go. So I can interpret this graph as the reactants have some amount of energy, and I essentially have to, I like to think of it as climb this hill. And then once I've reached that amount of energy, then I can go down the other side and products are formed. And so from where I started to the peak, that is my activation energy. Every reaction is going to have a different activation energy. So if I look on this endothermic one, I'm starting down here at the reactants and my hill is much higher. I have to go all the way up here. So this reaction would have a higher activation energy than the one on the left. So let's scroll down. The delta H can also be calculated by taking the kilojoules for the products and subtracting the kilojoules for the reactants. And delta H is always going to be calculated this way as products minus reactants. Just to remind you that when I have an endothermic reaction, that means that delta H is going to be positive. I'm putting energy in. And when I have an exothermic reaction, that means delta H is negative. Energy is leaving the system. And so we don't think of it as like plus and minus. We think of those signs as only indicating which direction the energy is flowing. Is the energy flowing into the system? That would be endo. If energy is going into the system, or is energy flowing out of the system? That would be exo. And that's what that positive and negative corresponds to on the delta H value. Positive means into the system. Exo negative means it's leaving the system. Another vocab word that comes up from time to time is the energy of the activated complex. And that's just what we call the top of the peak. So when I have my activation energy diagram that looks somewhat like this, my activated complex is going to be this spot here at the top. And you can think of that as a transition state. And that is the kind of point where the reaction is happening. Bonds are being broken, new bonds are being formed, and you can think of it as the hump to get over to products. And so the top of the peak has a special name. We call it the transition state or the activated complex. Now the energy needed to get to that point, that is our activation energy. So let's look at some example problems. On number 1, it says, consider a series of reactions having these reaction coordinate energy profiles. Place an X on each diagram where the transition state occurs. So again, that transition state is just going to be the top of the peak. Next, they want us to rank the reactions from fastest to slowest and then explain our reasoning. So I'm going to be looking solely at my activation energies. So my activation energy is the energy from here up to the top, which in each diagram is actually labeled for us. So remember, the smaller activation energies means the reaction is going to potentially go fast. So smaller activation energy equals faster reaction. So I would say that reaction 1 would be fastest. Then 3 has a 20 kilojoule activation energy. And then 2 has a 25 kilojoule per mole activation energy. We kind of just answered part C already. Part C is wanting to know the activation energy. So for 1, that's that 15 kilojoules per mole. For number 2, that's 25 kilojoules per mole. And for number 3, that was 20 kilojoules per mole. For each one on part D, they want us to identify delta H and whether it's endo or exothermic. So I'm going to erase and get some clarity in my diagrams. The delta H is going to be the distance between my reactants and my products, and that is actually also labeled to us on each graph. So for reaction number 1, my products minus my reactants give a negative 10. So that's going to be my delta H value is negative 10 kilojoules per mole. And remember, when delta H is negative, that tells me it's an exothermic reaction. Similarly, on number 2, the distance between the reactants and products is already labeled. So delta H is going to equal negative 15 kilojoules per mole. And remember, it's exo when we have a negative delta H. But for reaction number 3, my reactants are here and my products are here. So this is actually an increase. I'm going up. So delta 8 is 5 kilojoules. And since it's positive, that means that this is going to be an endothermic reaction. On number 2, it says, based on the energies of the table, which of the following diagrams best represents the change in energy as the reaction proceeds? And we have H2 plus Cl2 goes to 2 HCl's. And this is kind of tricky because we actually haven't talked about this type of problem before, but that doesn't mean we can't figure it out. So in order to break a bond, I need a certain amount of energy, and that's called the bond energy. It's listed over here on the table. So to break an H2 bond, I would need 430 kilojoules. To break a Cl bond, I would need 240. And if I add those together, I get 670 kilojoules. So that's how much energy is needed to break those bonds. Well, to form HCl, I need 430 kilojoules. But notice I have two HCl's. So I actually am going to take that times 2 and I get 860 as my products. So remember, delta H equals products minus reactants. So if I want to figure out which graph matches, I can take 860 minus 670 and I get 190, and that is a positive value. So I can actually eliminate already this choice and this choice because they both have the delta H value listed as 240. Out of the two that are left, I'm going to pick the one where my delta H is shown as a positive value. So remember, positive means energy is going in, and I should see an overall increase, which would be this last one. On the first one, I'm seeing it go down, which means in that one, that would have been a negative 190, meaning that was exothermic. And that is it for the introduction to energy profile diagrams. Thanks, y'all.